Hi. In this video, we'll be exploring some of the basic properties of vector spaces. For convenience, let's make the convention that V always denotes a vector space. In the definition of a vector space, we required the existence of an additive neutral element, and for each element in the vector space, we required the existence of an additive inverse. I already hinted in past videos that these elements are uniquely determined by their defining properties, and this is something we'll prove now. So the first proposition says that any vector space has a unique additive identity. Let's give a proof. Let's suppose that 0 and 0 prime are both additive identities of a vector space V. The goal of this proof will now be to show that 0 and 0 prime are actually the same element. Because 0 and 0 prime are both additive identities, we have by definition the following equalities. First, V plus 0 is equal to V for all elements V in the vector space V, and this is because 0 is an additive identity. And second, V plus 0 prime is also equal to V for all elements V in V. But now, 0 prime is equal to 0 prime plus 0 by the property in A. This is because 0 prime is an element of the vector space, so if we add the element 0 to 0 prime, we get back 0 prime. We can now switch the order of the addition by the commutative property that is satisfied by our vector space, and then apply equation B to get that 0 plus 0 prime is equal to 0. This is because 0 is also an element of our vector space V, so adding 0 prime to 0 gives back the element 0. We conclude from the above equation that 0 prime is equal to 0, which is what we wanted to show. Since we've seen that the additive identity is unique, we can now introduce a symbol for it. So we denote the unique additive identity by the symbol 0. Next, we'll show that every element in a vector space has a unique additive inverse. So let V be such an element in our vector space V, and assume that W and W prime are both additive inverses of V. By definition, this means that V plus W is equal to 0, and also that V plus W prime is equal to 0. But now, W is equal to W plus 0, because 0 is the additive identity in the vector space V. And using property B, we can now rewrite 0 as V plus W prime. By associativity, this is the same thing as W plus V plus W prime, bracketed in the other order. And by commutativity, we can switch the order of V and W in the brackets. However, by property A, what's in the brackets is just 0. And adding 0 to any element in the vector space V gives back that element, so 0 plus W prime is equal to W prime. Looking at the beginning and end of this chain of equalities, we conclude that W is equal to W prime. So what we've shown is that given two elements that are additive inverses of V, those two elements are actually the same element. So in fact, additive inverses are unique. This again allows us to introduce some notation. First, we denote the unique additive inverse of V by minus V. And second, we can define a subtraction as follows. We simply set w minus v to be, by definition, w plus minus v. Our next proposition concerns the relationship between the 0 in our field f and the 0 in our vector space. It states that if we scalar multiply any vector v by the 0 element in f, then we get back the 0 element in our vector space v. Since we use the same symbol 0 for both the additive identity in the field f and the additive identity in the vector space v, it's important to watch out when 0 appears in an equation. In this case, it's clear from context that the 0 element on the left-hand side has to be the 0 element in the field because we're scalar multiplying it with a vector. Since the result of scalar multiplying a scalar by a vector is again a vector, we know that on the right-hand side of this equation, what we have to have is an element of v. So the 0 there has to be the 0 in our vector space v. Let's give a proof. Let v be an element of v. Then 0 times v is the same thing as 0 plus 0 times v, because 0 is an additive neutral element in the field f. And now using the distributive property, this is the same thing as 0 times v plus 0 times v. Now adding minus 0 times v to both sides of this equation gives 0 times v minus 0 times v is equal to 0 times v plus 0 times v minus 0 times v. But of course, the left-hand side is by definition equal to 0. And on the right-hand side, we get that 0 times v gets cancelled out by the minus 0 times v, and we're left with 0 times v. And so these two are equal, and we've shown the proposition. In the next proposition, we ask a similar question, namely what happens if we scalar multiply the 0 element in the vector space by some scalar a. And the proposition states that if we scalar multiply 0 in the vector space by any scalar a, we get back 0. The proof is very similar to what we've seen before. We let a be an arbitrary element of our field f. Then a times 0 is the same thing as a times 0 plus 0, where these zeros in the bracket are now the additive identities in our vector space v. As in the last proof, we can apply the distributive property to get that this is the same thing as a times 0 plus a times 0. Recall that there are actually two distributive properties in a vector space. The first one says that addition in the field distributes over scalar multiplication, and the second one says that scalar multiplication distributes over addition in the vector space. So here we're using the second of these distributive properties, and in the previous proposition we used the first one. We can now add minus a times 0 to the above equation to give that 0 is equal to a times 0. And this is exactly what we wanted to show. Our final proposition concerns how minus 1 interacts with scalar multiplication. It states that scalar multiplying a vector by minus 1 gives back the additive inverse of that vector. To show this, let's take an element v of v. We now want to show that minus 1 times v is the additive inverse of v. So we do this by seeing if minus 1 times v satisfies the defining property of an additive inverse of v. So we need to check that v plus minus 1 times v, that this is 0. We can rewrite the v in this expression as 1 times v by the vector space axioms. We now apply the distributive property in reverse to get that the above expression is equal to 1 plus minus 1 times v. However, since minus 1 is the additive inverse of 1 in our field f, this is just 0 times v. And we saw in the previous proposition that 0 times v is 0 for any vector v. So the above shows that minus 1 times v satisfies the defining property of an additive inverse of v. But we also saw that additive inverses of v are unique. So since minus v is also an additive inverse of v, we have that minus v has to equal minus 1 times v. And this proves the proposition. To conclude, let's summarize what we've seen in this video. First, we saw that any vector space has a unique additive identity and unique additive inverses. Then we saw how special elements of our field and vector space interact by scalar multiplication. We proved that the 0 in our field multiplied with any element v in our vector space is equal to the 0 of our vector space. In a similar fashion, if we scalar multiply the 0 element of our vector space by any element a in our field, we get the 0 element in our vector space. And finally, if we multiply any vector in v by minus 1, we get back minus v, which is the additive inverse of v. All of these properties should seem very intuitive, and they'll help us when we have to do arithmetic with vectors. That's all for today. Next time, we'll be starting a new topic and looking at subspaces of vector spaces. I hope to see you then.